Here are some more solved examples using Taylor's polynomial in different situations. So we are going to see some of these problems that are recommended in your book, so I encourage you to actually try to do the work yourself also to get comfortable with the type of questions. So here we have a task which is to use a polynomial of degree 3 that is centered at pi over 2 and use it to estimate cosine of 80 degrees, and that estimation needs to be correct to 5 decimal places. So first thing, we need to find the coefficients for the polynomial, Taylor polynomial degree 3, which means we need to definitely to compute up to third derivative, and also to estimate the error we will need the fourth derivative. So that's why in this list I have the function and then all the 4 derivatives, and since we need to be centered at pi over 2, we evaluate function and the derivatives at pi over 2. So this will produce a pattern for the coefficients. So we are not creating the entire Taylor series, we are only asked to produce the Taylor polynomial of degree 3. So with these coefficients we could generate the entire series, is not a problem, but it's not asked, but I still put it there so you see an example of the Taylor series centered at pi over 2 for the cosine, so you have it as a reference. Now in order to find the approximation, we will need to convert the 80 degrees into radians. So basically we need to use this formula here to get the radians. So what we get here is 1.396 radians. So if I evaluate, so this series is good for all x, if I evaluate it at exactly 80 degrees, which is 1.396 radians, I get this expression. So the series that from which I'm going to take the polynomial degree 3 looks like this. So here I will have a number, obviously, because pi over 2, I will compute it and I'll subtract these two numbers. So the result of subtraction is here, negative 0.1745. So our cosine at 80 degrees or 1.396 radians is equal to this series. Now we are asked to get an approximation with polynomial degree 3. That's nice. We would like just to make sure that also the error is respected, because they ask error with 5 decimal places that are correct. So just to verify the error, so the associated error for the polynomial degree 3 is smaller than this expression here, and indeed it satisfies the condition, since this is 1.3 to 10 power minus 6, so this satisfies the requirement of having the result correct to 5 decimal places. So this is just a verification to make sure that the polynomial degree 3 is actually going to give us the correct precision. So now the polynomial degree 3, so we get it from this series here. So basically we have only 2 terms, which is nice, and the approximation for the cosine will be produced by this polynomial degree 3 is the same value, obviously. So we just plug x equal to this number into the expression here and we get the value. So there's some computation to be done here using the calculator. So this is an approximation of cosine of at 80 degrees, so 1.396 radians. Now we just computed the error and we figured out that it is correct to 5 decimal places because the error was smaller than 1.3 to 10 power minus 6. So this was important just to verify that actually our approximation satisfies the requirements from the question. So we use the polynomial of degree 3 centered at pi over 2 and we got the estimate, and this is the error is smaller than the number here, so it respects the requirement of 5 decimal places. So it was just important to verify that. The easy part is obviously just to plug the number into the polynomial, but we need to make sure that actually the result we get respects the requirements of the question. In this case, obviously, we used the approximation for the error, right? So this was an alternating series, so we used that. Okay, another question is a similar question. Here we need to use the polynomial of degree 4, so Taylor polynomial of degree 4, and find expand it at pi over 6 for the function sine x. So we use sine x to generate a Taylor polynomial degree 4 centered at pi over 6. So again, we will need to compute some derivatives. The second part of the question asks us to estimate the accuracy of the approximation that we just found with the polynomial degree 4. And we need to find that approximation estimate of the accuracy on the interval 0 pi over 3. So that will be something important to take into consideration. We will see how to do it, and obviously we are going to use Taylor's inequality for that. And the last part asks to find an estimate of sine of 38 degrees, and that estimate needs to be correct to 5 decimal places. So obviously we will be converting the degrees into radians. So let's see step by step what to do. So the first part was to find the polynomial of degree 4 for the function sine of x that is centered at pi over 6. So we need a couple of derivatives. So since we need polynomial degree 4, definitely we need 4 derivatives, and then for the error we need the next derivative also. So we compute the derivatives for the sine, all 5 of them, and we evaluate the derivative at pi over 6. So this way we get the coefficients for the polynomial, and we know that the error will be involving the 5th derivative. So we are just preparing the situation for when we need it. Our x is between 0 and pi over 3, so we quickly evaluate cosine, the values of cosine in that region. So it's bounded between radical 3 over 2 and 1. So this will be useful for the error estimate. So the polynomial degree 4, Taylor polynomial that will be used to approximate sine of x, is given here. So it's centered at pi over 6, and we use the coefficients that we just computed with the formula for the Taylor polynomial. So we just simplify a little bit all these factorials to have more compact notation. So this will be our approximation of the sine x by the polynomial degree 4 centered at pi over 6. So it's not really complicated. Now the next step is to estimate the error, and here we are given the interval 0 pi over 3, so we need to estimate the error for x that is in this interval, and we will use Taylor's inequality for that. By the way, if you just look at here, this polynomial is part of the series obviously, and it is not an alternating series because you have positive, positive, then negative, negative, then it will be positive, positive again, and negative. So it's not an alternating series. So we, in this case, we cannot use the alternating series estimate because this is not an alternating series. So it's important to realize that. So that's why the only option in this case will be use of Taylor's inequality. So sometimes when we have alternating series, we can use Taylor's inequality or the alternating series estimate at our choice. But in this particular case, we see that this polynomial is part of the series, and that series is not alternating. So our only option for the estimate of the error is Taylor's inequality. And here we remind the definition or the estimate for the error using the Taylor's inequality. So if we use polynomial degree n, the formula says that error is smaller than some number m divided by n plus 1, so n plus 1 factorial, and here the power is n plus 1 also. And the number m is a constant, is a number that is bigger than absolute value of the derivative n plus 1 of our original function. And we will see how to find the estimate for this. In our case, we have polynomial degree 4, so n is 4 for us, so we will need to find an estimate, an upper bound for the fifth derivative on the interval 0 pi over 3. So x lives in this interval here, so that will be a very important information to use in order to find the m. So we have our polynomial degree 4, so n is 4, the interval is 0 pi over 3, so the fifth derivative will be used in order to estimate the error. So the fifth derivative is cosine, and since x lives in 0 pi over 3, we can compute a couple of values and see that actually cosine varies between radical 3 over 2 and 1 in the interval 0 pi over 3. So this means that the cosine for these values of x is smaller than 1. So since cosine is the fifth derivative, so the fifth derivative is smaller than 1. So we are going to use that information here, because the formula said we need m that is bigger than the fifth derivative in the interval. So here we found the fifth derivative was cosine, and it was squeezed between these two numbers, so cosine was smaller than 1 in that interval, fine. So we are going to use that here. So our m is 1. So now using the Taylor's inequality, when m equal 1 and n is 4, so by the formula is 4 plus 1, and here power is 4 plus 1, and our series was centered at pi over 6, so we get this expression. So the error associated to the polynomial degree 4 is smaller than this expression here for all x in the interval 0 pi over 3. Good. So basically now we need to estimate this value here for x's living in 0 pi over 3. So this for x between 0 and pi over 3, x minus pi over 6 is smaller than pi over 6. So that way we have found m first, then we find now the upper bound for this expression here. How? Well, we see values of x vary from 0 to pi over 3, so we try to compute a couple of values to see what's happening here. So we saw that all the values of x minus pi over 6 are smaller than pi over 6. So basically now we have an estimate for the error. So the error is smaller than 0.0003. So using the polynomial degree 4 for x in the interval 0 pi over 3, our error is guaranteed to be smaller than 0.0003. And again, we found upper bound for the fifth derivative on the interval, it was 1, and then we found the upper bound for the expression here, x minus pi over 6, for x's between 0 and pi over 3. So that upper bound was pi over 6. And the last part is to estimate the value of the sine at 38 degrees, and that should be correct to 5 decimal places. Okay, let's see how to do it. Obviously we will use the Taylor's inequality because that's our only option here, and this is the formula obviously. So we have x from 0 to pi over 3, so that this was our estimate, so this formula is still valid. Just we need to convert 38 degrees immediately into radians, so we get something close to 0.66 radians. Okay, so the error for x equal 0.663225. Well, we replace x by this expression, we plug it in, so we get this value here. So 0.666 divided minus pi over 6, so we get this value here. Okay, so we now need to get an approximation correct to 5 decimal places. Okay, so we need to see what type of polynomial we need. Maybe it's polynomial degree 4, maybe 5, maybe 6, we don't know yet. So we need to estimate what is, we need to find n actually. So we know that the error at our point of interest, 38 degrees, is smaller than this value here. We need just to find n. So how do you do that? Well, you try to put some values of n and by trial and error see what you get as an error estimate. So if I take n equal 3, I get this value here, which is 0 with 4 zeros 1. So that's not good because the requirement is 5 decimal places. I have 4, so n equal 3 is not gonna work for us. If I try n equal 4 and I put it in the formula, I get a much better estimate because this one is 4 times 10 to the power minus 7, so this definitely satisfies the criteria of 5 decimal places. So in our case, n equal 4 is going to give us an approximation that will satisfy the criteria. So we are going to use polynomial degree 4 to actually get the approximation of sine at 38 degrees. And the error will be smaller than 4 to the power 10 to the minus 7. That's the guarantee. So now we are going to use our polynomial degree 4 that we get, and we just replace x by the equivalent of 38 degrees, but in radians, obviously. So we just plug x equal to this in the entire formula. So here I just simplified a little bit the situation because we have x minus pi over 6. So since x is all this number here, we need to subtract this minus pi over 6. So the work is done here. So that's what I call h, just this number, because if I keep copying the number, it's gonna be very, very long for nothing. So this is our h, which is the argument here, x minus pi over 6, for x equal the equivalent of 38 degrees, but in radians. So we plug it in and we use our calculator to compute the value, so we get this expression here. So the approximation of sine of 38 degrees is 0.61566. So this we know is good. It satisfies our criteria, which was 5 decimal places. So this one is even a little bit better. It gives 6. So that's how you use actually the Taylor's polynomial of a given degree to approximate a function at certain point. So basically you use your Taylor polynomial centered at, in this case, pi over 6, and then we are obviously close to pi over 6 with 38 degrees, and the approximation is quite good in this case with polynomial degree 4. Another example is very similar actually. So we have a different function, 1 over radical x, and we need to use polynomial of degree 3 centered at 4 to approximate the function. So it's not a lot of work actually, it's quite fast. And we need to estimate the accuracy of the approximation by this polynomial degree 2 for x's in the interval 3.5 and 4.5. And obviously for this estimation we will use Taylor's inequality. So in this case we have the task to find the Taylor's polynomial degree 2, so we need to go up to 2 derivatives, and then we need a third one to estimate the error using the Taylor's inequality. So the question was to find the polynomial degree 2 centered at 4, so that's why we evaluate function and the derivatives at 4, and now we just use the formula to find the polynomial of degree 2. So Taylor's polynomial of degree 2 is given here with the coefficients that we just computed, and then when we simplify things a little bit, we get this expression. So we here have 2 factorial, so basically we just multiply by 2 the 128. So this is the polynomial of degree 2 that is approximating the function 1 over radical x. Now the next task is to find an estimate for the accuracy when x lives in the interval 3.5, 4.5. Again, we are using Taylor's inequality, so we have the same formula as before, and our goal is to find an estimate m as an upper bound for the derivative. So in our case, it will be, since the polynomial is degree 2, it will be the third derivative for x's between 3.5 and 4.5. So that's the first task. So we have polynomial degree 2, interval is here, third derivative we already computed, and for x's between 3.5 and 4.5, the values of the third derivative in absolute value are between the lower bound here 0.0097 and 0.0233. So the upper bound on the third derivative here is 0.0233. That's what we are going to use in the Taylor inequality. So the Taylor inequality here gives us a formula. Now this is good for x between 3.5 and 4.5. So now we are just going to make sure that we get an estimate upper bound for the x minus 4. So obviously the distance between the two bounds and 4 is 0.5. So that's why we have here that this expression here is smaller than 0.5 to power 3, right, for x's between 3.5 and 4.5. So if you put 3.5 minus 4 is 0.5 negative, but in absolute value is 0.5, and if you put 4.5 you will get again 0.5. So obviously this is an increasing function. So we have the estimate for this value here for x's between 3.5 and 4.5. That helps us put all the numerical values in the formula and get an estimate of the error. So in this case, with the polynomial degree 2, actually we get 3 decimal places of precision. So the work was not difficult because the question asked only for the polynomial degree 2, so the derivatives were not long to compute actually. And the error we see is quite decent still with the polynomial degree 2 only. So that's very good. A similar question, but for the function log ln 1 plus 2x, we need a Taylor polynomial of degree 3 and it needs to be centered at 1. So we'll compute some derivatives. Since the degree of polynomial is 3, we need definitely 3 derivatives, and we need the 4th derivative to estimate the error. And the second part of the question is actually find the accuracy, so estimate the accuracy for x in the interval 0.5, 1.5, and for that we will use Taylor's inequality as usual. So here again we compute the degree of the polynomial is 3, so we compute the 3 derivatives, and we will compute the 4th one later on, and we need to evaluate it at 1 because that's the center of the series. So the estimate, the approximation of the function for the polynomial degree 3 is given here. So this is our Taylor polynomial degree 3 that is approximated the function ln 1 plus 2x. Now again the same procedure to estimate the accuracy of the approximation. We have the Taylor inequality and we need to find m, which is the upper bound for the derivative, the next derivative. So in our case it will be 4th derivative for x is between 0.5 and 1.5, so that will be the first task. So the fourth derivative we computed, it gives this. So on interval 0.5, 1.5, the fourth derivative is squeezed between 0.375 and 6. So the upper bound for the fourth derivative on this interval is actually 6. So m is equal 6 in the formula. Okay, so we just plug 6. Our n is 3, so we have 3 plus 1, so 4 factorial. Upstairs is 6, so we simplify a little bit. So that's why we have this expression here. And now the last step is to find the upper bound for x minus 1 for x is between 0.5 and 1.5, so that's obviously 0.5. So that way we have our error smaller than this expression here. So you see in this case the approximation is not phenomenal. You only have one decimal place with the polynomial of degree 3 for our approximation. Another type of questions that we can have is related to, again, approximation by the Taylor polynomial, but this time we would like to know what is the interval for x for which the error is smaller than certain fixed number. So the question is normally given in such a way that we give you a function and it's part of its Taylor series, so we give you some Taylor polynomial of certain degree, and in this case sine is alternating series, so this was at x equals 0, so basically this is a Maclaurin polynomial of degree 3 and it's alternating obviously. So the estimate of the error will be given by the next neglected term, so in absolute value. So the error is smaller than x to the power 5 over 5 factorial. So that's normal because the next term in the series, Taylor series for sine would be plus x to the power 5 divided by 5 factorial, and we are using alternating series estimate obviously because the Maclaurin series for sine is alternating, and we need our error to be smaller than 0.01. So now we just do some algebra to find the interval for x. So since error needs to be smaller than 0.01, well, we do some algebra, and our x actually needs to be smaller in absolute value, smaller than 1.037. So the interval for the x is negative 1.37 to 137. So this means that the polynomial here given, the polynomial degree 3, that is approximating sine centered at 0, gives us accuracy of 0.01 for all x that is in the interval negative 1.037 up to 1.037. So for x is in this interval, the error will be smaller than 0.01 when we use the polynomial of degree 3 to approximate sine x. So it is a decent size interval for very little effort. So here is a similar question, so the same polynomial, all we do is ask for a bigger control on the error, so we want a better precision. Here is 0.01 and the next requirement is 0.001, so we actually want a much better precision, 10 times better precision. So the procedure is the same. We have our estimate for the error, so the upper bound is given by the alternating series estimate, and it needs to be smaller than 0.001, so do some algebra and we find the interval here. And if you compare, so when we require error to be smaller than 0.01, we have interval, you see, with 1.037, but when we ask for a much better approximation, the interval is smaller. So here is 1.037 for the error 0.01, but for the error 0.001, then the interval is much smaller. It's with 0.654, right, plus minus. So this interval is much smaller than the other one, but we have a better precision, right? So that's what we in general noticed with the Taylor polynomial approximations. They are very good when we are close to the center of the series. So which means if we require better precision, so smaller error, the interval will be shorter, and the interval is centered obviously here at 0, because we are using Maclaurin polynomial here. So it's important just to realize that if you want better precision, your interval on which the polynomial is decent approximation will be smaller. There's a price to pay. So if you want a precision that is lower, you get x within larger interval. Better precision, shorter interval. So similar question here. Again, we are going to use alternating series estimate for cosine, and expanded obviously at 0. So this is Maclaurin polynomial degree 4 in this case. It is given, and the requirement is that the error be smaller than 0.005. And we use the alternating series estimate because this is part of the alternating series for cosine. So that will be x to the power 6 over 6 factorial. And this needs to be smaller than the prescribed error of 0.005. So doing some algebra, we get an interval. So for all x's in this interval here, the error is guaranteed to be smaller than 0.005 when we use this polynomial degree 4 as an approximation of cosine x. So I can plug different values of x in this interval and get a decent approximation for the function cosine x just by using this polynomial here. Now the similar exercise, if I want better precision, so this is 0.005. If I want precision 0.001, so it's 5 times better. What happens? Well, so we do the same algebra. What happens is that the interval shrinks. So you see here interval is 1.238 plus minus, and here is 0.9467. So our interval is smaller when we require higher precision. So for the x's living in this interval, the error will be smaller than 0.001 using this polynomial degree 4 to approximate cosine. Okay, so if we want better precision, interval will be smaller. Similarly, in this case, we have tan inverse. So the approximation of tan inverse by the polynomial degree 5 is here. So this is part of the alternating series, obviously, for the tan inverse, centered at 0. And here we want error to be 0.05. So error needs to be smaller than that. Alternating series estimate for the error term is the next neglected term. So here we have 5 x to the power 5 divided by 5. So next guy is x to the power 7 divided by 7. And that needs to be smaller than 0.05. So with a little bit algebra, we find the interval. So for all x's in this interval here, the error will be smaller than 0.05 when we use this polynomial degree 5 as an approximation for tan inverse. Okay, again, since this is Maclaurin polynomial, it's centered at 0, right? And again, if we want a better precision, so here the requirement was 0.05. Now the new requirement is 0.01, so 5 times better precision. Well, the interval will shrink. You see, here we had 0.86, here we have 0.68. So the interval is a little bit smaller when we require a better precision. So those are, in general, the ideas that we need to explore when we are given a Taylor polynomial to approximate a given function. So sometimes we are asked to find the interval in which x will live and to guarantee a certain error. So this is the procedure. And sometimes we are asked to use polynomial certain degree and then find the approximation or the estimate of the error using that polynomial. So those are typical questions. So I will encourage you to go through the process of actually trying to do it yourself. You have the solved problems here, but it's important for you to actually do the work just to get some practice.